news now. There's been a security breach at one of the larger companies that provides title insurance and settlement services.
Hackers can get into online accounts.
It's news of a massive cyber attack affecting all of these institutions from.
Encryption is the art and science of securing information, ensuring that it remains private and confidential when transmitted or stored. In an era where our lives are intricately woven into the digital landscape, the significance of encryption cannot be overstated. Imagine sending a sensitive email, making an online purchase, or accessing your bank account information. All these activities involve the exchange of personal data. Encryption serves as a digital shield, safeguarding our privacy by transforming this information into an unreadable format that can only be deciphered by those with the appropriate key. In essence, it's like sealing your message in an impenetrable envelope that only the intended recipient can open. In today's interconnected world, where data travels across networks and continents, encryption is the linchpin of cybersecurity. It protects our communications from prying eyes, be they malicious hackers or unauthorized entities. Moreover, encryption plays a pivotal role in securing your financial transactions. When you enter your credit card details to make an online purchase, encryption ensures that this information is shielded from cybercriminals who may attempt to intercept it. This not only safeguards our finances, but also fosters trust in the digital economy. Encryption is a silent guardian of our digital lives. It enables secure communication, protects our financial transactions, and upholds the fundamental right to privacy in an age where information is both powerful and vulnerable.
RC4 Encryption is a symmetric key stream cipher designed by Ron Rivest in 1987. It's known for its simplicity and efficiency in generating a pseudo-random key stream, making it suitable for various applications. The RC4 algorithm operates in two main phases: key scheduling and pseudo-random generation. In the key scheduling phase, the algorithm initializes an array of a specified amount of elements based on the provided key. It then performs a series of swaps in the array, creating a unique permutation. This ensures the dependence of the array on the key. The second phase, pseudo-random generation, involves iterating through the data while swapping elements in the array. The algorithm generates a pseudo-random byte at each step, which is then XORed with the corresponding byte from the input data. The XOR operation produces the encrypted or decrypted output, which is key for password management.
To begin our project, we wanted to simulate our RC4 project to demonstrate the encryption and decryption of strings. To accomplish this, we use Python. Let's quickly break down our concept. The function RC4 takes a key and data as input parameters. It initializes an array S with values from 0 to 255 and performs key scheduling to create a permutation based on the key. The function then generates a pseudo-random stream by iterating through the data, swapping elements in S, and XORing the result with the pseudo-random byte.
However, this is just a software-based implementation of RC4 encryption. Using Verilog and an FPGA for implementing RC4 encryption would introduce several differences compared to a software-based implementation in Python. Let's explore these differences in terms of speed, memory, and processing. FPGA implementation allows for hardware acceleration of the RC4 algorithm. Unlike a software-based solution where instructions are executed sequentially by a CPU, an FPGA can process multiple operations in parallel. This parallelism can significantly increase the speed of encryption and decryption. FPGAs operate at high clock speeds, providing the potential for faster data processing. The clock frequency determines how quickly the FPGA can execute each operation. FPGAs often have dedicated on-chip memory blocks that they can use to store lookup tables, intermediate results, or other data needed during the RC4 encryption process. This can enhance performance compared to a software implementation that relies on general-purpose RAM. FPGAs can be designed to perform parallel memory access, reading or writing multiple memory locations simultaneously. This can optimize memory access patterns and improve overall performance. Implementing RC4 encryption on FPGA using Verilog can offer advantages in terms of speed, memory efficiency, and processing parallelism. The parallel nature of FPGAs makes them well-suited for cryptographic algorithms like RC4, where many operations can be performed concurrently.
Our whole project is consisted of 5 modules so far. First one is the top module, the register, which is the memory, 2 encryption and decryption modules, and our login. The top module just takes care of all the data flow and the finite state machine of our project, which I'll dive into later. The register just takes our 2 inputs, our user and our password, and saves them there. Encryption and decryption, so pretty self-explanatory, just encrypts and decrypts those user and password 8-bit datas, and the login allows for access to the FPGA, so we can hard code the rightmost switches on the FPGA to be data and the leftmost switch to be next state. Next here we have part of the decryption code snippet, not decryption code snippet, the top module code snippet. Here's just the FSM for our project. It just starts at an idle state to make it easier for ourselves. Then the next state is store user. The user will input a 8-bit user. It'll get sent to the register. The next state is store password. The user will input a password. It'll get sent to the register. After that, the next state is to encrypt both those 8-bit numbers. The state after that is then a check password or login state. The user will then put in the user and password numbers that they remember. And if it's correct, it'll verify. And if it's incorrect, it'll tell you and it'll be unsuccessful. The next code snippet is just part of the decryption module snippet. Here, I just want to emphasize the permutation array is key. What happens here is just a permutation array specific to the 8-bit numbers gets created. And then this raveling creates sort of ciphertext conjuncted with the key and the plain text that the user made. And then when this permutation array is created, it uses the key and XORs each array to unravel back the ciphertext into decrypted text. And that line of code just happens right here. Then this next slide is just a simulation showing of our entire project. The first one is just a case where I used 5.4 as my username and AA as the password, and then I was asked again for the user and password. And after I did those successfully, the login success was successful, and the decrypted output was again my password AA. And then there's just 2 more examples there to show the verification of that.